Welcome. This is our first module in a global sustainable energy class, and we start at the beginning as appropriate. A history of energy. I go back to when we just had human power, just us. Whatever we could do in a day is whatever got accomplished. We carried things or used very simple machines. So how much work can a single human accomplish? How about this young lady here carrying water on her head with an earthenware pottery-style jug? You know, look at that photograph. That's a modern photograph. That's not an old Kodak overexposed reds and colors. That's a modern photograph. So that's how people live now in many, many parts of this world. So let's take a look at some of the things and where we're going with that. So first of all, we got to get some units straight in our heads. A watt is a unit of power. We named it after a guy. You know how typical scientists are. They name it after some famous guy. So James Watt, inventor of a modern-day steam engine, not the first one, but the one that really took off, and we'll talk about that in a second. He has a unit of power named after him. Power is energy per unit time, and the unit of energy is joule. So a watt can be expressed as a joule per second. So if a human being can average, and I'm not talking about an athlete that can really put some output out for a short period of time, but I mean a regular human being, 8 hours a day, can average about 75 watts of power output. So what's the daily total of this work? Daily output, as a simple equation there, is 75 watts, or joules per second, times how many seconds in an hour? That's 3,600 seconds in an hour. Times 8 hours a day. A daily output of a human being is about 2.16 megajoules per day, where the capital M stands for mega or million. Another way to look at this is a block of energy consumed over a period of time. It's sort of like a light bulb in your house. So if I turn that light bulb on, a 100-watt incandescent, because we haven't changed over to energy-efficient light bulbs yet, that's another module. If we run that for a 10-hour period, I can multiply that out. The answer is 100 watts times 10 hours is equal to 1,000 watt-hours. Now watch how that's noted. Look at the units carefully. It's not watts per hour, it's watt-hours on the same line. Dissecting the units, a watt is a joule per second. Multiply this by time, that's in hours. So we have joules per second times time. If we use a suitable conversion, getting rid of the time differential in seconds and hours, we're left with joules or just energy. So really what you're doing when you buy 1,000 watt-hours from the utility or 1 kilowatt-hour, you're just buying a block of energy. So on a human scale, an output of 75 watts per day for 8 hours a day gives you 0.6 kilowatt-hours per day. That's a basic human output. So we lived that way for a number of years, thousands of years actually, until we domesticated animals. We thought, wow, you know, if I can get this cow to do work for me, he's just sitting there munching grass, how about if I get the cow to do work for me? So they harnessed the early cows, domesticated those animals, and come to find out the early harnesses did not transmit the power efficiently. And a cow was only worth about 4 humans. So at this point, it still was cost effective. It's really terrible to treat it in economic terms, but the way societies worked back then, it was still cost effective to have slaves rather than cows. Well, years go by, centuries probably, and they came up with a better harness for the cows that transmitted power more efficiently, and so cows were worth about 6 human beings. At that point, it's more effective to own a cow. And off we go to domesticated agriculture. So simple machines throughout our history, we go through time and we end up with, this is a disc harrow pulled by 2 donkeys with a guy sitting on a seat. Human-powered machines or pumps, a little hand crank water pump in the front yard of the farmhouse, or this donkey-pulled disc harrow. Where do we compare? How do we compare that in what we do today? Just to throw some numbers at you, I'm going to look down here because I can't memorize everything, but we use about 18.3 million barrels a day in this country, United States of America, of oil. Now, a barrel of oil is 42 gallons, so I can work that out to how many gallons are used per day in this country. Well, we also have about 316 million people in this country. So if I work that out, it's about 2.43 gallons per day per person of crude oil. My own little pot of crude oil I have every day. Well, a gallon of crude oil is about 140,000 BTU. That's another unit of energy, British thermal unit. So I can work that out. convert it all back down to our early human output of 0.6 kilowatt hours a day. With the proper conversions, I come up with that 2.43 gallons a day I get is equal to having about 166 of my own personal slaves to do whatever I want them to do. Imagine that, 166 people doing whatever you want. I mean, kings of old didn't even have that kind of luxury, and yet we take that for granted. Many areas of the world you can see, and some of us have come from these areas and have traveled to these areas, so we see this. There's a couple of cows pulling a single row plow. The person behind that looks like a pretty big field for those two cows and that one person. Next to it we have farm carts, donkey carts to bring merchandise to and from the farms, and again, animal-powered vehicles. Over here we have in Holland, it looks like wind power, early wind power. So we've gone from humans, then to animals, now to early simple machines. The wind power in Holland they used to pump water out to drain the land, also to grind grain. Early designs were inefficient, but hey, the fuel was free and plentiful. Now we don't have a picture, but another early model of a wind power vehicle, or not vehicle, but machine, was a Greek sail wing. Excuse me, they're working through a cold. Now out in our great American West, you know, they first thought it was a desert. You know, come to find out there was water underneath that desert and a lot of nice soil. This was an American Jacobs aeromotor, early water pump that was driven by wind. Next to that we have a Persian windmill. Wind came from one direction and that was a vertical axis machine. That's about 1,500 years old. How about water power? Well, how many times you see cities spring up? I mean, look at a map. They're on the borders of oceans, on the borders of rivers. It's because you had water power for energy and transportation. But here we have an example. The picture to the right, the drawing is an overshot water wheel where the water comes in over the top. And I think you can't really tell, but the picture, the actual picture, I think that's stream flow, where the water flow, it's not a dam, but the force of the water moving hits the bottom of the water wheel. And that can grind grains or even run a lumber mill to saw wood. So if we take a look at this, early mechanical output of a windmill is about 1.5 to 10.5 kilowatts. Well, that's a bunch. Think about a human being. That was 0.075 kilowatts, 75 watts. How about the early water wheel? The mechanical output might have been 1.5 to 3.8 kilowatts. Again, quite a bit more than early single human or even cows. In 1888, Charles Brush came up with a early wind power machine. Output was 12 kilowatts. I mean, completely dwarfed by what we do today, but still a huge output nevertheless. Now, those were all driven by renewable energy, wind and water. How about engines? Now we come into the point where we talk about engines. The first steam engine was a Newcomen engine. It was a guy that invented a simple steam engine designed solely to pump water out of coal mines. Didn't matter it was inefficient, because you just shoveled in more coal. You're right there at the mine. It had a simple up and down motion and a very inefficient design, but still it worked and pumped water out of the mines. Well, Watt came up with, and correctly it's a Watt-Boulton steam engine. They were partners, but Boulton seems to be forgotten these days. But Watt-Boulton steam engine had a couple of really big changes and advantages. They separated out the steam condenser from the steam boiler, so you could do the hot things in one place and the cold things in another place. That made it faster acting and much more efficient. They also developed a crankcase and a flywheel to convert that up and down motion to rotary motion. Now you have what we know as today as an engine with rotary motion. So now you can do things like develop mobile vehicles. That was yet to come. So to summarize this, an early working laborer, and even laborers today, about 0.075 kilowatts output. An ox, about 6 times that, or 0.45 kilowatts. Early wind power, 1.5 to 10.5. Early water power, 1.5 to 3.8 kilowatts. And holy cow, now we're off to the races. Newcomen steam engine, 15 kilowatts. Watt-Boulton, 25 kilowatts. A diesel engine, now we come into the late 1800s, and diesel comes up with a diesel engine, and its output is 10 kilowatts. Now we got something going for us. Let's compare. An ox is equal to about 6 workers. That's 0.45 kW divided by 0.075. That's an ox for an individual labor. The largest early wind power devices represent the output of about 140 laborers, 10.5 kilowatts versus 0.075 kilowatts. The Watt Bolton steam engine, holy cow, 333 people. Now we're really cooking. But wait a minute, we drive around in cars, many of us do. For example, a car with a 134 horsepower engine, that's about 100 kilowatts, is equivalent to the output of over 1,300 individual laborers. Think about that. Every time you get, I forgot my milk, so I have to go back out to the grocery store, a separate trip, get in my car, and harness 1,300 laborers to get me to that grocery store and back. What an astounding level of progress. We'll see where it gets us in the next modules.